And our next speaker is Matias from PSI, and he will present the integration of Bliss data in the Beck system.
Okay, so yeah, can you hear me? It's fine. So good morning, everyone. So yeah, I'm very happy to present today the part of the work I'm currently doing about integrating ESRF Bliss data with PSI Beck. So for once, we'll start with a slide about the speaker, which I never do normally. But yeah, okay, I'm a software engineer with 20 years career at ESRF within the Beamline control unit. And I've been Bliss project responsible for the initial development phase and deployment for 6 years. And yeah, I'm on sabbatical leave since last January, and I could join forces with PSI staff in the Beck development team. So to participate to their development. And so if you know me from previous conferences with my ESRF hat, today I have my PSI hat, even if I don't have a Swiss flag spinning off my head, okay? So the talk outline, first I give an introduction to Beck, then introduction to Bliss and Bliss data. And the third part is about integrating both and the conclusion. So introduction to Beck. So yesterday, my colleague Klaus already made a nice introduction to this project. But basically, it's the new experiment control system for SLS2 beamlines. It's an in-house development at PSI, heavily inspired from Blue Sky from an SLS2. It's open source software with BSD license, and there's a link to the code repository hosted on the PSI GitLab. So Beck is a PSI answer to the challenges of modern beamline experiment control systems. So there are 6 main areas. One is data acquisition. So PSI is EPIC's territory for this. And also with some in-house solutions for 2D detectors, for example. Then there is live data visualization and graphical interfaces. Also data processing, data archiving, interaction with users, so via command line interface, scripts and everything. And also linked to SciCat and data policy and electronic logbooks. So, but when we talk about Beck itself, when you download the package, basically this is what you get is inside the right boundary. So the technical choices behind Beck, so we can summarize with 6 points. So it's all written in Python. It has a services-oriented architecture. It makes heavy use of Redis as data buffer and also message broker. And interesting thing is that it's using OFID from Blue Sky for devices control. And so there is a sub-project called OFID devices in Beck. For the shell, it's based on IPython. And all the graphical widgets, I mean, all the graphical interfaces are built with Qt. So there is a specific project in the Beck. It's a sub-project called Beck Widgets that already been presented before by Jan on Monday, and also there are some posters. So basically, the architecture of Beck is very modular. So the cornerstone is really the Beck core library, and it brings all the bits and pieces for the other service for the services. So the services are independent processes. And they rely on the library to communicate with Redis and to communicate between them. So we have the device server, which gives access to the hardware through OFID. And then on top of that, we have the scan server, and the scan bundler. So those two allow to have a queue for executing scans and also gives access for the data. The file writer is saving the data, and also there is a data processing and the SciHub. So SciHub has nothing to do with SciHub, the website. This is the service to connect to the data catalog and the logbook. And from the user point of view, there is the Beck shell and Beck widgets application. So under the hood, how does it work? I mean, there is a Redis connector, which is a Beck core library object to communicate with all services. And it's using Redis as the message broker. So with this object, it's easy for any client or any service to exchange data with the other services. So basically, they have operations like storing in Redis, publishing events or streams, or events in streams. And in fact, this object with threads reads the data, incoming data, and executes callback. So it's very easy with this object to connect to the system. So the messages are very well defined. So they all derive from the same Beck message base class. And there is a validation with Pydantic to ensure that the messages really correspond to what is expected. So basically, we can think about a scan server, which is emitting a device instruction message for the device server. And in this case, it will pass through, thanks to the Redis connector, it will be conveyed to the endpoint as a Beck message, so serialized and deserialized. So in this little example, we can see that there is a trigger action from the scan server to the device server. So now I will pass to the second part of this talk, which is the introduction to Bliss and Bliss data. I can't talk about Bliss data without talking about Bliss first. So it's Bliss is the Beamline instrumentation support software developed at ESRF since 2016, and has been designed especially for the EBS upgrade, so for the new Beamlines of the 4th generation light source. And it's like Beck. It's a Python library with batteries included, let's say, like it's known in Python world. So it brings a lot of tools with a command line interface, a web terminal, a configuration application, live visualization, data access, file writer. One particularity, well, it's not a particularity, but it's a sequencer as well for any kind of acquisition procedures. And the particularity is that we have built-in drivers, which comes from I would say, our spec legacy. And so we mainly control hardware through built-in drivers or Tango, for example, 2D detector or any other kind of device through Tango. And I put the link to the latest Bliss article, so if you want more information about Bliss, you can just click on this link. So to give a bit of a big picture of Bliss, so this is how it enters in ESRF ecosystem, let's say. But we can see that there are differences compared to Beck. The library is all the core features are within the same library, and there are much less servers around. But one important point to notice is Bliss data. So Bliss data here. So it receives data from the system and allows to as clients like Flint for the data display, for our Nexus writer for writing files, Evox for we had a great presentation yesterday about Evox, so it's for real-time data processing and workflows, and also graphical interfaces through Daiquiri. So Bliss data is really a central component of Bliss. So Bliss data, it's a separate package, so it's easy to install. It has limited dependencies. Like any Python project, you can just pip install it. There is also a Conda package. And it serves two purposes. It's publishing data as a producer, and also with the same library, same package, you can retrieve previously published data, so in the consumer side. The support technology is Redis, with the addition of extensions like Redis JSON and Redis Search. So basically, actually, yeah, in Bliss data, everything is built with the concepts of scans and streams. So Bliss data defines a model to represent scans and provides the acquisition streams to push data. So you can see it as in fact, it's on top of Redis streams, but it provides much more features and makes it very suitable for data access in our context. And also, it's handling scans of scans. So if we want to have a little schema about what's happening during data acquisition in Bliss, so we have data blocks, which we call data events, in fact, that goes to streams, in fact. So here we have two different acquisition channels. So it can be, for example, a temperature, and this can be a position. I mean, you can, whatever you imagine. And it emits those data blocks to the stream. And first, the scan creates a scan structure, and then the streams are filled with the data. For big data, which is today mainly 2D, we just publish references, and I come to this in the next slide. An important feature of Bliss data is that it's decoupling the stream contents and the data itself. So streams are filled with data events, but data can be elsewhere. So you have two. So the data events are those mailboxes, let's say, and data can be directly in the event, or you have to order the pickup somewhere. Yeah. So there are two cases. Either it can be shipped with the event, or it's too large, or it's stored by the acquisition in its own file, for example. And then in this case, we only emit JSON events. And in this case, in order to interpret the events, there is need for a Bliss data plugin to reference or dereference the data. So now let's focus on integrating Bliss data with Beck. So Beck distributed architecture and nice, clean message passing makes it easy to interface with any of the components, or to add a new component connected to existing services. In this proof of concept that I'm doing, I wanted to minimize number of processes, copies, and all this. So I decided to stick to a more direct implementation, which is basically this one. So the idea is to publish Beck scans with Bliss data, to have access to ESRF HDF5 writer, to have access to the display tool and processing tools, but not with a separate process, directly with the library imported by the scan server and the device server. So here I have a video, which can maybe start. No, maybe. No. Oh, how does it work? Sorry. It's embedded in the PDF, so on my computer I see it. Yeah?
No, oh. The PDF with Acrobat.
Ah, okay, so can I do it now? Yeah? I'm sorry. Can you move that? Yeah, because it's too bad if we don't see the video. Yeah. Voilà, I can continue from here. It's okay.
I'm not sure it runs.
No, wait, up. Okay, I'm allowing the video. So now we can see, so here I'm starting Beck command line. Maybe it's a bit fast. So I'm starting Beck command line. And when Beck command line is starting, it's connecting to all the services. So at the moment, the Beck services are running, except the Beck file writer, because I have the ESRF file writer, and you can't write to the same file the same thing at the same time. Okay? So this is the only process from Beck that is not running is the Beck file writer, and replaced by the ESRF file writer. And so when Beck is starting, it's waiting for the GUI to start. The GUI we're talking about here is Beck widgets that has been presented before. It's the one that is given as the default graphical application for people using Beck. So this is what we see here, Beck widgets. Of course, at the moment, it's empty. And it's starting Flint, which is the ESRF tool for data visualization based on Bliss data. Then I'm moving things to another workspace so we can continue with the demo. Yeah, and yeah, so here I'm loading the devices in back configuration. And from here, I can access some simulation devices. So for example, a motor, a beamline position monitor, intensity diode, or things like that. And now I'm going to start a scan with those 3 elements from this motor from -50 to 50. I will reduce a bit number of steps. OK, I'm starting scan. So the scan is running in back. And we can see in back widgets that we have the plot. Here, I'm switching. So this is Flint behind. And we can see that it's showing the same data, of course. So this one is the big widgets is taking data from back mechanisms, and the Flint is taking data from Bliss data. And then we can see also the MCA 1D curve, and then we can play with Flint to use Flint to display curves. Yeah. So once the scan is done, then we can use another ESRF tool called Silex View to see the file. So the produced file corresponds to the ESRF HDF5 Nexus format. And here we have a hold that has been recorded. So we can see the curve, okay, and the 1D data as well, okay. Yeah, so this is it. So so what's next? So the next steps for this integration to be finished is to connect to the 2D data. So at PSI, as I said, there are 3 different ways to connect to 2D data. So thanks to the Bliss data plugins, it's relatively straightforward to imagine to have a plugin for each kind of data provider, and either to get, so those, they all provide frames through ZMQ, or they get the right files. So we can then write a Bliss data plugin that will automatically, like we do at ESRF with our own system for 2D detectors, which is called Lima. Then we can do the same and either get data from ZMQ or from the file. And this is all handled by Bliss data plugins. And also, there is some EPIX devices that are writing data directly to files. So then in this case, we can again write a Bliss data plugin in the hope that maybe it's the same HDF5 format, for example, or could be another format, and then the plugin deals with that. Because the plugin will receive events which tell where is the file or where is the device to connect to, and then it will interpret this to bring data for the clients. So as a conclusion to this work, or to this talk, not this work, it's not finished yet. I would say that we have nice distributed architecture, which provide entry points for plugging new services or extending parts of the system, thanks to the Redis connector, the back messages. But also we can see that Bliss data can easily be embedded into any data acquisition system. And because there are generic concepts like scans and data streams, which are very simple and corresponds well to the business domain, I would say. And there is ongoing work at Alba, tests at least, to see how it goes with Sardana. At DESY, there is also work with Sardana and also Blue Sky in the frame of the Rocket project. And at PSI with Beck, which is this talk. So what's next? So there is quite some work to have Beck plus Bliss data complete with the 2D detector support. Because, of course, if you use Tango and Lima, and Bliss data, you have it. 2D data is straightforward. It works out of the box. But as I said here, it needs to be to have a plugin. And we probably Bliss data people should write a better specification of the schemas and more documentation. But this is easily doable. I would say, as a final word, what I really want to say is that with small development teams as we all are, in fact, and there is existing software, it's very valuable to try to mutualize software. So, in particular for data handling, visualization, processing, archiving, all these can be more shared, I would say. So I hope that things like this data can help with that, and at least to have some kind of interoperability to better serve our users community. And I would like to finish something that I really want to talk about. I'm exceeding too much. Oh, I'm sorry. Okay, but this is really important. So if you want, you can look on the slide. There is a new thing. I mean, it's not really new, but now it's really compatible with Bliss data out of the box. It's called KV Rocks, and it's a Apache Foundation-backed project. And it's an implementation of Redis-compatible protocol with registers and Redis.json on top of RocksDB. So it's targeting fast disks like SSD and NVMe. So projects like that can be a bit of a, let's say, a game changer to have, for example, a lot of memory on as an NVMe or SSD disks, and without changing anything, having a very big buffer as people want. Voilà, so I'm done. Thank you. Thank you for your attention. Sorry.
Thank you, Matias. Unfortunately, there is no time for questions, but this is the coffee break. So please, come to Matias and ask all the questions. So before you leave, there is one important message, is that we are going to do the photo during the break, the coffee break. So where is the...
Just in front of the coffee.
Just in front of the coffee. So general, the conference picture. Yeah.
The quicker you get there, the quicker you get your coffee.
Yeah. Okay, thanks.